Thanks for having me on stage. Thanks for the intro. Thanks for the intro, Andre. Thanks for having me, everybody. Like Andre said, I'm one of the co-founders and the CTO at Yugabyte, and here to talk about extending PostgreSQL to Google Spanner architecture. So, I mean, everybody's familiar with PostgreSQL, and it's becoming one of the most popular databases out there, right? Everyone's picking Postgres for running their applications. But imagine you had something that does everything Postgres does, but can also run in a cloud native fashion, right? Run in the cloud, tolerate failures, can do scale out, and you can deploy it across zones and regions in a geographically distributed way. So that's what we're trying to do with YugabyteDB, and let's dive right into it. Just a quick note, please keep the questions flowing. We'd like to take questions during the talk. So if there's any, and depending on the nature of the question and the depth, we can either defer it to the end, but please keep your questions coming. That makes it more interesting for everybody. Okay, so quick introduction. What is YugabyteDB? YugabyteDB is an open source database, so you can check it out on GitHub also. But primarily, it's a distributed SQL database, right? That brings up what is distributed SQL. Well, like I was saying, imagine a database that can do your SQL and SQL, that can support SQL and can do ACID compliant transactions with 3 extra properties, right? It can tolerate failures, so it's very resilient to failures, whether it's node failure, zone failure, what have you. It's massively scalable, which means you can add nodes to handle more queries, and it's geographically distributed, so you can deploy it in a multi-zone fashion or a multi-region fashion. Now, YugabyteDB is a distributed SQL database, which is built with high performance in mind. So all C++ from top to bottom. It's cloud native, so that means you can run it on Kubernetes, VMs, bare metal, anywhere. It doesn't really have any external dependencies. And it's fully open source. So just like PostgreSQL, it's fully open source under the very permissive Apache 2.0 license. Okay. As a project and as an open source project, these numbers are much bigger even compared to where we were last year because it's another 6 months. But we've been seeing good growth in the community. It's now being deployed under reasonably big scale for mission critical applications across a variety of users. So these users are a few users that are serving billions of operations per day using YugabyteDB for their production workloads, and they use it so they can tolerate failures and scale out as needed. We're an open source project, so if you folks are interested in the talk or interested in the project, show us your support. We love your stars. Give us a GitHub star. Join our community on Slack. We'd love to talk to you if you are interested in distributed SQL. All right. With that out of the way, let's jump right into what it takes into transforming PostgreSQL into a Google Spanner-like architecture. Okay, when we set out to building YugabyteDB, we had the same thing that any reasonable person would ask, why are you building another database? There's so many of the databases out there, you're not doing anybody a favor, right? So we said that we don't really want to reinvent the database language. We wanted to keep it completely compatible with PostgreSQL. So we said we want to make it so compatible that we want to reuse the upper half of PostgreSQL. So we support everything, right? Like your stored procedures, your triggers, all your data types, and so on and so forth, all the complex queries and other features that it supports. And we wanted to make the changes in such a way that we can continue to stay up to date with PostgreSQL as time moves, right? Over time, we want to enable migrating to either newer PostgreSQL versions or by migrating PostgreSQL features into YugabyteDB. We started out with PostgreSQL 10.4 codebase as the upper half, and we then graduated to Postgres 11.2, right? Now, whether it's going to be easy to keep doing this or whether we need to port features from Postgres, we'll take a look later. And finally, we said this has to be built for the cloud, so it has to be cloud native, no single point of failure, ability to automatically tolerate failures, run in containers, and zero downtime, things like rolling software upgrades, machine reorg, so on and so forth. All right. When we started out, there were 2 prominent cloud-native SQL databases. It was Aurora and Google Spanner. And we kind of hybridized the upper half of Aurora with the lower half of Google Spanner, right, in trying to build Yugabyte. So Aurora is exceptional in its SQL support, right? But Aurora is also great at doing fault tolerance. But if you want to do horizontal write scalability, that's something Aurora is not built for. You have to scale up your node that handles all your writes. And if you hit the biggest node that's available to you, you'll have to figure out how to manually shard your data. On the globally consistent side, like with Aurora, you can do a variety of techniques to replicate data globally, but it wouldn't be consistent across the different geographies. So if you want to do globally consistent writes and reads from multiple nodes with strong consistency, some caveats that you have to be aware of, right? And on the Google Spanner side, all of these are covered. Like it is horizontally write scalable. It can do geo-distributed deployments and scalable reads from anywhere. But it doesn't have as much of a SQL support. Like it's lacking. Like for example, Google Spanner only recently added foreign keys, which are extremely critical in the RDBMS world. And if you look at other features like triggers or partial indexes, those are all missing from Google Spanner. Now with Yugabyte, we said, hey, we're going to do what Aurora does for the upper half, which is reuse PostgreSQL, and we're going to do what Google Spanner does for the lower half, which is make it horizontally scalable and ability to have geographically distributed deployments. Okay, so in order to achieve this, we said we're exactly going to do this. We're going to have an upper half, which is our query layer, which reuses PostgreSQL code, the upper half of the PostgreSQL code, and we're going to have a lower layer called DocDB, which is completely inspired by Google Spanner and distributed store that does strongly consistent writes and can do distributed transactions and so on, right? So at a high level, these are the two components that go into building YugabyteDB. Okay, if you want to think about how our approach to building this database was, you can kind of think of it as we started with a single node PostgreSQL code base, right? And at a high level, you can split this code base into two parts. The upper part of the code base is the PostgreSQL query layer, which does things like, you have the postmaster and then parsing, analyzing, rewriting, planning, and executing the query. So which is all the RDBMS feature portion of PostgreSQL. And you have a lower storage layer. The storage layer is the one that takes care of storing data on a single node, right? Like how do you deal with, like, this is the write ahead log component, the background flusher, or like the vacuuming and so on and so forth. So we took this and we said we wanted to retain the upper half of PostgreSQL, and the lower half of PostgreSQL, which was a single disk, we wanted to replace it with a distributed store. So the first step of the journey was to extend PostgreSQL to distributed SQL, right? Like this is the step where you're now able to make the upper half of Postgres almost stateless and work against a different distributed store underneath, right? The second phase was, like, if you notice what the first phase at the end of whatever we accomplished here is that all of the data now has to flow to the query layer from the storage layer underneath, right? Which can make things very inefficient, because even if you do, for example, a simple thing like give me the maximum value of a column, you would need to pull the entire table's worth of data into the upper half of the node that's handling the query and then process it, which is very inefficient. So the second step, the second phase, which is, and these different phases are in different levels of maturity and completion. The second phase is to take a subtree and push it down into the storage layer below. So for example, in the same query where you want to select the maximum value of a column, you can push down the maximum value to the node or set of nodes or all nodes that would be responsible for the data in the table. And you would be able to execute some portion of it locally and then move only the results of that up to the top in order to do a second level aggregation, right? This makes things a lot more performant in a distributed system. So in order to do this, the query layer of Yugabyte, which is called YSQL, actually identifies the subtree to push down, which nodes to push it down, and then the executed result comes back, and then it works on the result of that the partial results from the various nodes. Okay, the third phase, which is in a little earlier stage, but is something that is making rapid progress, is to use things like table statistics-based hints, geographic location-based hints, and the fact that there's a network cost involved in going across nodes, and even rewriting the query plan to make it more relevant for distributed. So that you really get a better execution for distributed set of nodes, right? So that's really something that's in progress. Obviously, the advantage that YugabyteDB has is it has all of the infrastructure that PostgreSQL has to build on top of, right? Okay. In this talk, we talked about the three phases, right? The first phase was how to take PostgreSQL and distribute it. The second phase was how do you do intelligent push down of subtrees and what are some of the interesting cases there. The third phase is how do you rewrite queries to make it more efficient for distributed SQL, right? In this talk, we're mostly going to focus on phase one, which is how do you take PostgreSQL and convert it to this distributed Google Spanner-like database, right? And so we talked about the two layers. So first, we're going to look at the lower layer called DocDB, which is the distributed storage layer, and then look at the upper layer, YSQL, which is the the PostgreSQL derived layer that drives the queries and handles all of that stuff. Okay, at this point, I just want to pause real quick to see if there's any questions. Andre, if there are any questions that are worth taking now, or we can keep going otherwise.
Nothing so far.
All right,
nothing so far. Like everything's clear.
Okay, perfect. So the first, so DocDB, which is the distributed underlying store, which has Google Spanner-like properties, has to have a number of aspects in place before it can actually live like Google Spanner in effect, right? So we're going to take a look at what does it need in order for DocDB to perform like Google Spanner, right? The first thing is you need to shard your data. Now, DocDB, as the name indicates, is a document store internally. So the only schema it has is a key to document. And the data in a relational table is actually mapped into this document, right? And we're going to look at what it took for us to build DocDB. Now, the first thing that DocDB needs to do is to be able to distribute the data of a table across multiple nodes, right? So how do we do this? So we do this with something called internal sharding. So if you take a table, the data is automatically split into a group of rows, so into multiple groups of rows. Each of these splits or shards is called a tablet, right? This is automatic and transparent to you. So when you create a table, you can pre-create it with a certain number of shards, or you can control the number of shards, or you can dynamically split. So there's a number of different aspects to how you can achieve sharding in Yugabyte, but most of the time it is transparent to the end user. So in this example, we show a table on the left, and it's split into 4 shards on the right, each of them having a few rows. Now, how do you pick the group of rows that goes into each shard, right? Like that is called the sharding strategy. Yugabyte supports 2 sharding strategies. When you have very large amounts of data, you want to randomly spray your data by the primary key or a subset of the primary key across all nodes, because you're never going to do range queries, right? This is ideal for massively scalable workloads where you have many terabytes of data across the cluster, like for example, like an IoT style workload, or workloads where you have users as the first primary key, and you're probably not going to do queries across users. So it's like a great column or set of columns to distribute data evenly across the nodes in a cluster by. The second thing that Yugabyte supports, the second sharding strategy, is called range sharding. And this is very useful when you're actually going to do queries which are going to look up by a range, right? Like, so select star from table where key less than 10 and greater than 5. So give me all keys between 5 and 10. So for that type of a query, a range sharding strategy is really more efficient, and it supports both. Okay, so how do we extend PostgreSQL without breaking it to give this type of functionality, right? So let's take a look at that. So in the hash sharding use case, if you look at a logical PostgreSQL table, it'll have a primary key column. Like you can use a subset of the primary key columns, but in this example, we're simply going to assume there's one primary key column. And then you have a bunch of columns, which are the rows, right? Now, if you're using hash sharding, these columns are run through, the value of these columns are run through a hash function, and then that is stored into your entire key space, your table space, and that table space is cut into various tablets, right? So each of these cuts represents a shard or a tablet. You see the shard 1, shard 2, shard 3. Irrespective of the order of the primary key lexicographically in the table, it's distributed and sprayed across the different tablets in order to achieve uniform utilization of tablets, right? This is extremely beneficial. For example, if you have a table which has some information about, say, a city, right? Like you'll have cities maybe beginning with S, right? Like San Francisco and Seattle, which are close by and which typically would have a lot of data. So, and there may be very few cities with X, Y, and Z that have as much data, right? So this type of a sharding scheme really helps normalize the data, or normalize the size of data across and utilization of the nodes across the cluster. The way we achieve hash sharding is like, if you look at this create table statement, most of it is just vanilla PostgreSQL. But if you look at the last line that declares the primary key, you can actually declare like your typical, in typical Postgres, your sort orders for a primary key are ascending and descending, right? In this case, you can have a third sort order called hash, right? So you can just say it's a hash sorted, and that means it's going to completely get sprayed, and you don't really need to preserve the lexicographic order. I mean, note that in a single node RDBMS, this is less material because in PostgreSQL, it doesn't really matter if you're keeping all the data in one node, whether you hash or range or make it ascending or descending. So a default or just supporting ascending, descending should suffice. Okay, the second sharding strategy we talked about is range sharding. Keys are not sharded. They go like straight in the order in which they are written into the tablets. So depending on the workload, this could introduce hotspots if you're not careful, but there's automatic splitting to make sure data splits and reorganizes itself and spreads across the cluster. But anyways, this is the way you want to go if you have range queries, right? If you have things where you actually want to do select star from table where key less than some value and greater than some value. And this is for indexes, by the way. We're talking about primary keys, but it's true for any index, any secondary index on top. Okay, the way you achieve range sharding is, in this example, we just created a primary key, like everything else looks the same, but we say order ID ascending, and then you have product ID. I mean, obviously the default value for product ID in PostgreSQL would be ascending, so it would also be ascending sorted. In Yugabyte, the default, if the first value is left out, like if you didn't put ascending, is actually hash, and every other key is going to be ascending, or whatever the default in PostgreSQL is. If you want to override that, or if you want to be explicit about it, put ascending or hash or descending, when using YugabyteDB. Okay, so that's as far as sharding. So that tells you about how YugabyteDB actually splits data internally. Now let's talk about how it replicates and moves data across the various nodes in the cluster, right? So let's look at replication. So in order to replicate data across the cluster, the most fundamental building block is Raft consensus, right? That's what Yugabyte uses. Now, we had, like, when we started, we actually considered Raft versus Paxos. Like, a bunch of us in our team, we're quite familiar with Paxos also, having worked with it in a previous life. But we felt that we chose Raft for two reasons, which is that Raft is easier to understand than Paxos. Paxos is more of a broad set of rules, whereas Raft is an exact specification. And the second part is Paxos doesn't often mandate dynamic membership changes. It has to be something that people kind of build on top. And we just wanted it to be formally supported by the protocol. And dynamic membership changes are extremely useful, all the way from adding a node to a cluster, like if you want to expand the cluster, all the way to changing machine types. Like you can say, I'm running a 3-node cluster on machine type small. I now want to change the machine type to large, which means you need to move the entire like workload and set of queries running on the first 3 nodes to the next 3 nodes transparently at runtime, right, without any application impact. So, which is what we wanted to achieve. There is another talk that Heidi gave in this conference about Raft versus Paxos, so please check that one out if you want more details on this topic. But anyways, this is all the mention is in this talk about Raft versus Paxos. Okay, so we talked about how Raft is extremely important for a variety of different operations, including like a membership change dynamically, right? So let's look at how you add a node, which is an example of a membership change with ACID compliance without losing any data or introducing any inconsistencies in reads, right? So this is an example of, and every tablet in Yugabyte is replicated, right, using Raft. So every row, a group of rows is a tablet. A tablet is multiple tablets comprise one table. Each tablet is replicated across nodes using Raft, right? So that's really the setup here. So in this example, we have the 3 nodes on top, which have like the data in a 3-way replicated system of one tablet, right? And the way Raft works, it elects a leader, and that leader is responsible for handling all the reads and writes, right? So if you're adding a new node, it needs to get added into this raft group, right? Right now, there is a node which is a dotted cylinder, which has no data. It's a new node we are introducing. And we're going to see how this one tablet that is replicated across these 3 nodes actually includes this, like adds this new node in and then removes an existing node. Okay, so the first thing is when you add this node, that replication factor of this entire group, which was 3 before, now temporarily goes up to 4. So this group recognizes that, hey, I am supposed to replicate it 4 ways, and I have replicated it 3 ways, and one of the guys has no data, right? This is the same as if you already had 4 nodes and one failed and lost all its data and came back and it needs to get re-replicated. Okay, so the second step is automatically the data is bootstrapped into the 4th node, which means that the nodes that find, hey, this guy doesn't have the data, they're going to transfer or copy into, like using an internal protocol, they're going to copy the compressed data files, the write-ahead log, everything to this node and get it bootstrapped to a certain point and ask this new node to join the cluster, at which point it gets the remaining updates and gets completely caught up with the rest of the nodes. Now, the raft protocol, what it ensures is that all nodes agree on the values of, all the past values up to a certain point. So that means that the minute this new node enters the cluster, it needs to catch up with all the past data and then catch up on the delta, and it needs to say, hey, I'm caught up a certain value, right? So at this point, you have 4 nodes in the cluster, and each write will get replicated to 3 nodes, right? But this is only a temporary state. The next thing that is done is one of the nodes is removed from the raft membership group. So it's said like, hey, this guy is no longer a member, and change of membership is also a raft operation, right? So it uses this operation to say this new node is no longer a member of this cluster. It needs to no longer participate in replicating data, in getting data replicas, in voting for writes, so on, when it gets writes and so on. So it can then be safely removed from the cluster and it can delete its data. At this point, because the node was expelled from the membership, you now have 3 different nodes that store the data, and there's really no downtime, right? Like, because all of these operations are online. Now, we just achieved changing the nodes of a cluster, like from the original 3 to a new node. Like, we removed 1 node and added 1 node with 0 downtime for a single tablet. Now, if you repeat this for all tablets one after the other, then you'll have the entire table or tables moved into a new set of nodes, and the old node is removed without any downtime, right? So this is how Yugabyte, and all of this is done automatically. You don't have to manually sit through each of these processes. Okay, so in order for Raft to really work with our high performance goals specifically, there was a number of stuff that we needed to do, right? Number of enhancements that were needed, and which was also a very interesting journey. So the first thing is that if you're deploying, and you could have the 3 nodes running in 3 different regions. So the first thing is that multi-region Raft reads are really slow. And each read requires like a round trip to the majority. So you need to establish that you are the leader. So when you get a read, you need to make sure you're still the leader by talking to the other 2 guys and then responding. Now, the problem is if you're in faraway regions and you have to establish your authority each time, this could become a very slow database, right? Like, imagine if the latency between the regions is like 50 or 100 milliseconds, then every read is minimum 50 or 100 milliseconds, which is not a very high performing database. So to get around this, what we had to do was implement a Raft amendment, right? A Raft paper mentions this, but this is something that we had to implement, which is leader lease. So what leader lease does is, like you can see in this example that, oops, sorry, it went to the, yeah. So you can see from this example that the node B wins the leader election and becomes the leader of any tablet group, right? You can just say any tablet, B is the leader at this point, right? Now, the first thing it does is it replicates a lease period, and it says, hey, I am going to be the unquestioned leader for a certain point in time, right? And that point in time is shown here. So I am the leader. I have a lease up to a certain point, and B starts the clock and then replicates the data, right? Now, these guys, A and C, and this replication is done through Raft. So it's not like an external message. It is a part of the Raft protocol that it uses to replicate. So we know that the data is persisted in the cluster in a ACID compliant, fault tolerant manner. Now, when B gets the acknowledgement, B can then continue to serve reads. Like the minute it gets a majority acknowledgement, B can now serve reads without having to consult anybody, because it knows that everybody agreed they wouldn't become the leader up to a certain point in time, right? Now, A and C would actually, because they received the message a little later and responded, they would detect that B's lease is actually a little longer than whatever it originally was, and they wouldn't serve or do a leader election until they think B is no longer the leader if it fails. B continuously keeps refreshing its lease interval because there's continuous heartbeats between the nodes in the case of Raft. And what this lets happen is that now B can just serve reads without having to consult A or C, giving it high performance. Here's another twist that we had to do to really ensure performance and safety. So this is from the Jepsen testing report of Yugabyte. Yugabyte has been Jepsen tested. YugabyteDB uses monotonic clocks instead of the wall clock, right? Like our real-time clock, and that is the number of ticks that the software, the CPU does. So it's the clock monotonic in Linux speak, right? Clock monotonic raw. And it uses that. And the idea behind using that is it is less important for the purpose of leader leases to know exactly what time it is in that time zone. It is more important to establish a time window for which the lease is established, right? So you can have things like, for example, daylight savings kick in or NTP kick in. You can have various things kick in and adjust your real-time clock, which causes a lot of havoc when you're trying to actually make sure these lease values are appropriate. So the way Yugabyte does it is it uses the raw monotonic clock, which is the hardware clock, and uses time intervals rather than time values to detect how much time has passed. Finally, another enhancement was like Yugabyte does not take every write and put it through a Raft protocol, which requires a network round trip, which would make the database, again, not very performant in terms of throughput because it can only do a few outstanding writes at a time. The way it does it is once a Raft batch goes out, it then collects a bunch of possibly unrelated writes into a single batch and then gives them a stable transactional order inside that Raft batch and replicates the entire batch. So this gives it a much higher batch throughput. So you're able to do many thousands of operations per second instead of just a few hundreds, right? So you can do like tens of thousands of operations per second in YugabyteDB in terms of writes, specifically if you're using either in bulk inserts, like insert in an array of values, or even if you're doing a lot of point operations, YugabyteDB will combine them internally to make the operations more efficient. Okay, so that was it with the replication and storage and the sharding layers. Once again, I want to pause to see if there are any questions, Andre?
No questions so far. It seems like people are getting it. Like
awesome.
Everything's clear.
Okay. All right, great, wonderful, wonderful. But yeah, please do ask questions if you have any, folks. Okay, so let's go on to the storage layer. So we talked about how a table is split into shards, sharding. Each of the shards is called a tablet. We talked about how every tablet is replicated. So that's the replication layer, and how we use Raft and what are the performance optimizations we had done. So now let's talk about the third bit, which is the storage layer, which is how is data actually stored in each of the tablets, right? Like what do you do for that raw storage? And and that needs to be an efficient piece as well, right? Like, so how do we do that? Yugabyte uses a heavily modified version of RocksDB. And obviously for two reasons. Like RocksDB is very performant. It's written in C++. It's very good, ideal for SSDs. And we had to modify it to make it really appropriate and still high performing for the access pattern on top, right? Like the access pattern that we're talking about, which is like SQL tables and SQL queries. So the first transformation done to RocksDB was a set of changes to transform it from a key to value store to a key to document store, right? And that's because the set of, like a row in the SQL table is mapped to a document in DocDB, right? And if you just make one key value entry for each of the rows, it's going to be less efficient than if you're able to understand groups of values, right? So groups of keys and convert them into like one row, right? Sometimes you have to do row level operations. So The first change was to change a key value store to a key to document store. The second change was RocksDB is a database in its own right, even though it's a single node database. It has its own write-ahead log and its own multi-version concurrency control, right? But if you're using a Raft log on top, like which the Raft protocol on top to replicate data, Raft effectively becomes the write-ahead log for this distributed database. So that means that it's not a good idea to use RocksDB's write-ahead log because that causes double journaling. You'll have to write once at the Raft layer and then once again at the RocksDB layer. So the write-ahead log and the MVCC are both turned off in RocksDB and done at the higher level or at a slightly more global level inside DocDB, right? So these are some of the core changes. If you think about how DocDB encodes data, like because it's a document store, if you take a logical document as shown on the left, you have a document key 1, and then it has a subkey, which is itself a nested document. So you have a subkey and a 2 and 3 inside subkey 1. And then you have a scalar attribute subkey 4, which has a value. Each of them could have types and so on. The way this is mapped is into, like, this is at a very high level, and all of this may not always be used in every scenario, but at a high level, there is an initialization marker to say, hey, this entire document is reset or its type is changed or something, just to maybe even quickly delete the document. So there is an init marker, and there are entries for every subkey, right? So you could like, for example, delete subkey 1. You could delete or read just subkey 1 dot subkey 2. You could read subkey like 4 alone. Like, so you could do a lot of fine-grained operations in DocDB, which are upserts, updates, and reads at a attribute level. Now, all of this data, these subkeys, these rows that we talked about, have to actually get physically encoded into some storage format. So the way that's done is that the primary key of the tables go into what is called a doc key, or the document key, right? The document key is it's like a blob that is constructed from each of the primary key columns. So it's a concatenation of all of the primary key columns. And there's the hash shard and the range shard support for it built all the way at the storage layer. And then you have an area for the subkeys. Now, in the case of SQL, most of the time, there's going to be only like a single subkey in, like, you won't have nested documents, right? Like, you could have like a JSONB, for example, but if you take that out, if you just have an integer or a varchar or something, it's just going to look like a scalar value. So you will have a subkey, but you won't have too many nested subkeys. And finally, we also store the hybrid time, and we'll talk about why it uses hybrid logical clocks, but effectively it is the timestamp at which this update was written, so that when there's a scan process that comes in and wants to read data at a particular timestamp, it knows whether it needs to ignore this value or retain this value, right? Like, because what time was this key written is important, right? And finally, this is the encoding of a key, and it points to a value, which could have like a column, the actual column value, like whatever it is, stored in the PostgreSQL format. And it has, like, Yugabyte also supports auto expiry of keys, so that's why we have a time to live field next to it also, to know if the data has to get expired. All right. In order to get here, we needed to do a lot of performance enhancements to RocksDB in order to make the performance of DocDB better. And here's a few of them. So the logical architecture-wise, there is one of these RocksDBs that are modified for every tablet. So that means that in a single node, you could have many RocksDBs that coexist. So that means we had to share a lot of resources across the RocksDBs, right, and make them globally more efficient. And some of the things we had to do are a scan-resistant global block cache. So that means if you're doing a full scan and you're doing a lot of point reads, you don't want the full scan to completely wipe out the cache for your point reads. So it uses an arc insertion strategy to make sure that your high quality, multiple times read data is still in the cache, even if you do a full scan. We split Bloom and index blocks along with the data blocks to ensure that even if your file sizes get pretty large, you can still page in your metadata at a very granular value. Like, you don't have to read many megabytes of an index. It's always split and respects the minimum page size boundary. So that takes it a little closer to, even though it's an LSM store, it takes it a little closer to a B-tree-like, multi-block layout strategy. We have a global memstore limit, so you can have one table which gets a lot of writes and another table which gets a lot of reads. Memstores are the place where writes land, so you want to make sure that you're able to handle both and write size, and so give the table with more writes a larger memstore and the table with more reads a larger cache. So it's actually shares it across RocksDBs. And similarly, multiple compaction queues, load balancing across multiple disks, and so on and so forth. So there's like a lot of these enhancements. This is just like a smaller list. There's actually a much bigger list in practice. Okay, I want to pause here and see if there are any questions, Andre, before we go over to how all of this fits together in a deployment.
There is a question about range partitioning versus hash partitioning. If you want to address it now, or do you want to move it to the Q&A after the talk?
No, we can talk about it now. Yeah, I think if it's quick, we can
do
that now.
So the question is that from Denis Ursov, he looked at the range partitioning implementation in Yugabyte, and I quote, "If I understood correctly, the range partition tables could only have a single tablet, which limited the performance and scalability of such tables. If it's true, when do you have plan and timelines to improve scalability of range partition tables?"
Oh, that's a great question. So we've done a few things. We've allowed, we used to have one tablet. Now we introduced pre-splitting of a range partition table. So you could actually manually give the number of split points you want and get a multi-tablet range partition table. Now in the latest release, which is coming out in literally a couple of weeks, it's going to have automatic tablet splitting. So it's going to cover the two ways, you know ahead of time how you want to partition your ranges, and you don't know and you need to dynamically split, right? So both of those options are going to be, one of them is already there, the other is going to come out in a matter of a couple of weeks.
So what you're saying is basically if you start with single partition, the automatic splitting will still kick in and will split to as many partitions as you need, depending on the workload.
That's right.
Right?
And up to a maximum. So you can set a maximum to say don't split more than a certain amount. It's going to split based on, initially it's going to split based on data set sizes. And obviously this is something we intend to extend to do IOPS based splitting. So how hot a partition is. And we also have the ability. So these two, IOPS is in the future. Data set based is coming in 2 weeks. I mean, the code is almost done. The release is just coming out in a couple of weeks. And pre-splitting is already in, this. So you can annotate keys and say, I want my key range. For example, suppose you're doing the age of people, right, as your first primary key, and you want to do range partition because you want to run queries, give me everybody between 15 and 30 years old in your table. You could say hey, because I know that nobody's really going to be more than say 100 or 150 years old, you could just make 0 to 150 your total range, and then you could split by every 10 years or something like that. In the pre-split case. In the dynamic split case, you'll start with one tablet which deals with everybody, which is 0 to infinity, and practically you'll only have values from 0 to say no more than 150. And it's depending on how much data accumulates at each range of age, it's going to split those ages. So these are both coming. But great question, and thanks for following up and reading in detail. Okay. I get any other questions, Andre, or keep going?
This is it so far. Yeah.
All right.
Let's
cool.
Get back to
All right. Let's keep going. All right. So we talked about, again, to recap, we talked about how data is split in a table. Then we talked about how it's replicated. Then we talked about how that data is stored in each replica. Now we're going to put it all together, right? How does this whole thing come together and actually look like in a deployment? And how does the failover work? So here's an example of a table with 6 tablets, right? And we're just using 6 tablets because it's a lot of work to put this diagram together. So we can have a lot more in practice. We do have a lot more. We go by default for larger tables. We try to create 8 to 10 tablets per node, and that'll be very complicated in this diagram. So in this diagram, we have 3 zones, A, B, and C. They could be 3 different regions. They could be in different clouds. They could be on-premise and cloud. That doesn't matter. We have 3 nodes in each of these zones. So zone A has 3 nodes, zone B has 3 nodes, and zone C has 3 nodes. The placement policy we're going for a table that's being created is keep at least 1 copy of data in each zone, right? So that means each of the zones will contain a complete copy of the data. So in order to really understand what's going on, let's look only at zone A for a second, right? This table is split into 6 tablets, so each with a different colored cylinder, right? And all of those are spread, each copy is spread across the different nodes in zone A. Now, because we said that, and these are the tablets, right? And each tablet has to be replicated 3 ways. So you will find that there is a corresponding copy for each tablet in zone A in the other 2 zones, right? And you'll see that the tablets of the same color, which represent one grouping of rows, really enters into a raft consensus group, and they start replicating data. And one of those tablets is elected the leader, right? So this is roughly the split. So what this diagram shows is it's a 6-tablet table with a replication factor of 3 and a policy that says 1 replica per zone, right? And just a couple of these raft groups are shown here, like actually drawn out as an example, but all of the similar colors like the blues and the greens, they're all in raft groups as well. Okay, so a couple of things to note. Yugabyte tries to, there's a support of policies on where you want to place leaders, because if you recall, all of the reads and writes actually are done by the leader. By default, it tries to evenly spread data as much as possible. So tablet leader balancing is done firstly across zones. So you want to have each zone having roughly the same number of tablet leaders. Then it's done across nodes in a zone. I mean, in this example, we have only a few nodes, so some nodes don't even have leaders. But in practice, for large tables, you typically want to have enough leaders so that you have all nodes serving data. And it's done, and this is only one table in this example. You could have multiple tables, each of which are split into multiple tablets, right? So it's done for each table. So it's done across zones, across nodes, and for each table, right? So that you get the maximal impact or the maximal resource utilization for each table. You can, at runtime, actually specify policies which say, bring all my leaders to zone A or zone A and zone B. So you can kind of pin your leaders to some zones. But if you have an outage of that zone, these leaders will scatter. And when that zone heals, it'll come back, right? So it does things like that. All right, so let's look at what happens when a zone outage happens, right? So the first thing to note is that if you're using the database as a true database and not doing a read from a replica, then only the leaders are serving reads and writes, and the followers or the replicas are really not doing much except they're being a hot standby, right? So that when the failure happens, they're able to quickly take over. So the outage of an entire zone really, in this example, affects only 2 tablets of the table, right? The yellow one and the pinkish looking one, right? Those are the only 2 that are affected. The other 4 followers don't have any impact because they vote on writes, so they may have some impact on the write latency depending on where their locations are and so on, but it really has no impact on the operations of the cluster, right? Now, when a leader fails, a new leader has to get re-elected. It's a part of the raft protocol. In practice, what we have seen in a multi-zone single region deployment, which is what this is about, is about 3 seconds in order to re-elect a new leader, right? And there's no impact on a follower outage, like that's what we talked about. For the tablet leaders alone, the database is unavailable to take reads and writes for the failover window, which is the 3 seconds. And the follower reads are completely okay, right? So again, in this example, assuming that all tablets are evenly balanced across zones, a third of your database will be like rows will be unavailable for reads and writes for 3 seconds, and then automatically everything would start working. Okay, how does everything start working? So the failover of these zones, like failover of the nodes that fail, right? Like the failover happens as a part of the raft protocol. And depending on how far away these are, you need to tune the failure and the failover interval, right? Like if they're very far away, your RPC latencies would be pretty high, and so your failover windows would increase as well. But assuming that the RPC latencies are not too high, they're like in a few milliseconds, then you will be able to achieve like about a 3 second failover time. And these are all configurable, obviously, but we have good defaults. The second thing to note is that after the failure, it still tries to respect the load balancing policy. So by default, it tries to evenly spread the leaders across the remaining zones. So even if you find somebody that is heavily loaded, it would over time just smoothen it out, right? In this case, we lost an entire zone, and our placement policy said keep 1 copy of data in the zone, which means it's not much you can do. You don't have a node. But suppose you lost only node 4 and node 6 and you still have node 5, the system after 15 minutes, which is a configurable value, would try to automatically re-replicate the lost data from nodes 4 and 5 into 4 and 6 into node 5, right? Obviously, with a 2-node failure, you'll have node 5 as a bit overloaded. But if you just lost one node, then its data would get spread to the other 2 nodes, 50-50 split, right? And this is done automatically using Raft dynamic membership changes after 15 minutes. And the recovery and catch up is automatic. Once node 4 comes back, the data is redistributed back to node 4 in order to evenly balance data. Okay, so in a snapshot, if you just want the TLDR and all of that details are way too much, then the way Yugabyte works is on a node or a zone failure, you would have no data loss, so your RPO is 0. The minute the outage occurs, starts about a 3-second clock in a default deployment, and after 3 seconds, you'll have everybody being able to take reads and writes. For that 3 seconds, you'll have a subset of the data in the table not being able to serve reads and writes, and you can still do like stale reads, like reads from a follower, but you cannot do read from the leader. All right, I just want to make sure there are no questions, Andre, and we can go into the next topic, which is distributed transactions.
All clear on questions.
All right, great. Let's keep going. Well, I know that this is a great audience because the question was really good. So, so let's keep going. Okay, so for transactions, we looked at Google's Percolator. Again, not going to go into too many details of how Percolator works, but the most important takeaway is that Percolator uses a single timestamp oracle, which means so the single hardest thing about distributed or nothing easy about it, but one of the hardest things about distributed transactions is for getting many nodes to agree on a time at which the transaction is visible to the end world. So at what point is the transaction committed, right? So because there are so many nodes handling it, you would need a way to synchronize time. In Percolator, this is solved by saying, hey, let's everybody go to a single guy. That guy issues timestamps. There'll be no confusion in what the current timestamp is, right? Now, the problem with this approach is, firstly, it's not very scalable because everybody depends on a single timestamp oracle, irrespective of the size of the cluster, and it doesn't work very well for multi-region deployments, right? Like, so if you have 3 different regions that are far away, the timestamp oracle still lives in one region, and so you're now incurring high latencies for your transactions. The second approach to doing so is the Google Spanner approach, where the notion of time is decentralized. So in distributed time synchronization, like where the group of nodes involved in a transaction try to synchronize time amongst themselves, this is a harder path, but it is more scalable, and it can offer low latency multi-region deployments. And at a high level, it uses two-phase commit, like as the transaction core protocol. So you do a set of provisional rights, and once you acquire all your provisional rights, you flip the transaction to actually being committed. And we'll look at that. But we opted for this approach because geographic distribution was one of the core design principles of Yugabyte. Yeah, that's what it says. Yeah. So yeah, because of the distributed nature, we picked Google Spanner-like design. Okay, so let's look at how this works, right? Like at a high level, like we talked, it's based on a two-phase commit, and it uses hybrid logical clocks. And we'll look at what hybrid logical clocks are a little later, but let's look at how this the overall transactions work. In Yugabyte, transaction architecture is fully decentralized, so there's really no single point of failure or single bottleneck. So there's no timestamp oracle, there's no one entity dealing with transactions. It is distributed. In order to track transactions, there is a transaction status table, which is also a distributed replicated table across all the nodes. And any node can act as a transaction manager. So you fire off a transaction to a node, it handles that transaction for you. It puts an entry into the transaction status table. The transaction status table can have 3 states. It can be pending, committed, or aborted. And as the names suggest, pending is a transaction that's currently in progress. Committed means the value is written, you need to include it, and aborted means the value should be ignored, right? And we'll see why we need this. Reads are only served for committed transactions, right? The other two, like if it is pending, I mean, a transaction can obviously read its own data, but the rest of the world cannot read that data. And if a transaction is pending, you need to run some conflict resolution rules. If it is aborted, you just ignore it. If it is committed, you definitely have to serve it. Now, we talked about conflict resolution rules for transactions in progress. Now, conflict resolution depends on your isolation level, and isolation levels kind of determine the guarantees of who can see when a transaction is running and what are the semantics of a transaction, right? Yugabyte supports two levels of isolation: serializable and snapshot. Right? The serializable isolation level in PostgreSQL maps to the serializable isolation level in Yugabyte, and there's really no confusion because serializable just means there's a serial order of executing transactions, and it detects read and write conflicts inside a transaction. Right? Snapshot isolation takes a snapshot of the database at the time the transaction starts, and it can allow values to change at a future point, but not for values that the transaction writes. So it detects only write-write conflicts, and this maps to all of the other modes in PostgreSQL, which is repeatable read, read committed, and read uncommitted. The read-only transactions in Yugabyte are lock-free, so they don't really need to take exclusive locks or anything. And this is to ensure that there can be a lot of readers that can go in parallel. And it uses, it, however, has to follow, like depending on the actual nature of the read transaction, it may have to do the conflict resolution rules also. Okay, so let's look at how a distributed transaction works, right? So let's say the client is hitting any node of the server with, hey, update, set key 1 to v1, key 2 to v2. It's just written in pseudocode, right? Like you can make it any query you really want. The first thing it does is, and this is a more generalized diagram, like a lot of these hops are cut in practice by optimizations. The first thing it does is it goes to the transaction status table and it writes an entry for the transaction which says this is the transaction ID and it is currently pending. Now, in practice, tablet server 1, when it receives the query, always picks a transaction ID that falls locally, so you don't need that hop. And the transaction IDs are pre-created, so it's just as good as just flipping the value in a transaction to say it is pending rather than actually having to create the transaction status tablet. The second thing it does is for every key that it needs to update, it's going to write a provisional record. And these could be local, these could be remote, and these provisional records are written, which look like normal records, but they have a transaction ID associated with them. And so any reader coming in, if it hits a value which has a transaction ID associated with it, it's a trigger to say this is a provisional write. You don't know if you can serve this read. You need to go check with the transaction ID in the status table to see what the state of this transaction is. Now, if any of these writes encounter another provisional write, then that's going to be a conflict and it has to be resolved accordingly, right? So, but let's assume all of the provisional writes go through. Then the next step is to commit the transaction by going to the transaction status table and flipping its value from pending to committed, right? And if you hit, like, for example, some conflicts and you're not able to resolve them, it's going to go there and flip it to aborted, right? The final thing that's done, two things done, like number 5 is responding to the client saying, hey, your transaction is done. And in the background, it's going to flush, like you don't want a database where forever you go to the provisional record and you keep seeing this transaction ID and you keep chasing it. So it's going to flush the value of the committed transaction down to each of the nodes so that you're actually able to continue reads at some point in the future, like directly from that node, right? So it will rewrite this key 1 equals value 1 with the transaction bit associated. It's going to rewrite it with key 1 equals value 1 without the transaction ID, but with the transaction commit time, which is determined by the transaction status tab leader. I'm sorry. Okay. I'm going to go into the next topic, which is software-defined atomic clocks. But hopefully that gives folks an idea of how the transaction flow works. And we'll cover exactly how hybrid logical clocks work. Again, this is a deep topic. Again, happy to go into details with folks. But let's pause at the end of the next section to see if there are questions. Okay, so we talked about how the two-phase commit works, and we talked about how the transaction status leader actually picks the timestamp, right, of the commit. Now let's look at how these the keys belonging to different shards actually have to pick time. So if you're doing this update, key 1 and key 2 may belong to different shards, and they may belong to completely different raft groups. So in reality, your update that you wanted to do ends up looking like this, where in the worst case, you could have 6 different nodes involved in this transaction, right? and 2 of them being the leaders. Now, these updates should get committed at the same time. Obviously, we talked about this time being determined by the tablet leader of the transaction status tablet, but it doesn't mean that there could be nodes whose time is ahead or behind, right? And if you have nodes whose time is behind the time that was picked by the transaction status leader, then you'll get into trouble because they can commit new transactions on top and really overwrite the value, right? And so you'll get into all sorts of trouble there. So how do you get nodes to agree on time, right? That's really the question here. Well, in the case of Google Spanner, if you're deriving motivation from there, they tell you, hey, you need a couple of atomic clocks, just stick it all over the place, and you're kind of done, right? But in reality, and what do atomic clocks do in reality, right? They're highly available and globally synchronized clocks, but the most important property is they give you tight error bounds. So Google Spanner gives you about a 7 millisecond error bound. So within about 11 milliseconds, you will know that there's no node in the cluster that is syncing up to this atomic clock in Google Spanner's case, which true time is the service, right? There's no node that can be more than 11 milliseconds behind. So if you really want to make sure that you pick a transaction timestamp to commit, you just wait 11 milliseconds and you're fine. Everybody else has caught up, right? The problem, though, in real life is that people don't really have atomic clocks, right? And the physical clocks are rarely that tightly synchronized, right? Like, so you can use NTP, but NTP error bounds are much higher, like 150 to 200 milliseconds in practice. So what do you do? So hang on. Okay, yeah. So what Yugabyte does is it uses a hybrid logical clock. So it combines the coarsely synchronized physical clock through NTP with a Lamport clock, which is a logical counter internally. And in order to track, so every node has a physical component and a logical component in this hybrid logical clock. And it uses its physical component initially as the physical component of time, and it uses its logical component as every operation that it does, it keeps incrementing. But all nodes talk to each other, and if a node ever gets a message from a node with a higher physical component, then it's going to update itself to that physical component. So assuming that you have NTP to coarsely synchronize these physical components to make sure nothing runs away like many hours ahead, you'll find that overall the system is able to keep catching up to a time, and anytime there are causal relationships, you can track them through the system of physical and logical clocks, right? Now, these clocks are updated on every exchange, every raft heartbeat, every leader election, every data replication, a transaction coordinator coordinate message, any of these things, it exchanges this clock. But you'll find that you could still run into situations where there is no causal relationship and the physical component is not tightly synchronized. So you will run into situations where you could have something happen on a group of nodes, like let's say node 1, and you could have something else happen on a different group of nodes, or a node 2, and you find that you are not really able to tell which one happened first because the clocks are a little off and they have a gray area and there was no causal chain tying these two. So in such cases, Yugabyte detects these errors and will automatically cause one of these transactions to restart internally or throw a user-facing error, right? And this gets into the topic of how we want to handle this conflict, which is optimistic or pessimistic locking. And Yugabyte provides is mostly optimistic with some support for pessimistic or external locking. So it does a little bit of that. But bottom line is there is a gray area that it would have to determine. Yugabyte determines this transparently and figures out that you have to restart. And in practice, most of your workloads would not be so heavily contended. So this works out really well in practice. But you could always have pathological workloads where you cause a lot of contention and your latencies go up. Okay, so that's all I had. I didn't know how much depth we wanted to go. Again, this is also a deep topic, so happy to go into detail after hours, but wanted to see if there are any quick questions.
Okay, there is a question about
we just keep going. Okay, we just keep going. We can take it at the end, we'll take the question. Okay, so at this point, I wanted to get into the SQL architecture really quickly. So we talked about the bottom half. Now let's talk about the upper half. This is a very high-level PostgreSQL architecture. It has Postgres rewriter, optimizer, planner, all of this stuff. and we wanted to reuse the PostgreSQL layer. In fact, we tried to rewrite it, and then we figured this would take us forever to do it. It's just not possible given the 25 years of development in Postgres and the number of features that PostgreSQL has. So we said, let's take the upper half. Let's replace the lower half, which is the wall writer, background flusher, vacuum, all of that stuff. And we replaced it with the lower half of Yugabyte, which we just talked about so far, called DocDB, right? Now, obviously, taking the upper half of Postgres, which is wired to talk to its lower half, is not going to be without its set of changes. So we made a bunch of changes in a bunch of places, which would be enhancements and changes in order for it to talk to any node. So it needs to know about multiple nodes, needs to know about a different layout of data. So we made those changes in a bunch of places and tried to keep it as modularized as we could. But in practice, it's always very hard to keep it more than a certain amount modular. Note that we also changed the system catalog and all of those to be highly available. So what did we get? As a result, we have a stateless Postgres upper half that can talk to any node in the lower part. And you have the actual DocDB layer below, which we looked at in detail, right? So this SQL app can connect to any node. You can add or remove nodes anytime. And a failure of a node is not going to affect the app because the fault-tolerant lower half can actually survive the outage, like we looked at. We looked at failover and rebuilding and all of that stuff. And the upper half, is actually stateless. So if a node dies, it can always connect to a new node and is aware of the nodes in the cluster. The lower half of the stateless PostgreSQL layer is aware of all the nodes in the cluster and can jump to any node to get the value from. Okay, so we're going to go through a couple of flows. It's going to be quick because with all the background on the DocDB side, this is not going to get too complicated. So if you're creating a table, a YSQL is like the modified Postgres, stateless Postgres layer of Yugabyte, right? So a YSQL table, every table maps to one DocDB table, which is sharded. Every DocDB table is sharded or could be sharded into multiple tablets. Now, there are some exceptions here where you can map multiple tables from the YSQL side into a single tablet, but we're not going to go into that right now. The system tables, one of the surprises for us was there are 279 system tables in Postgres, and we didn't want to make 279 tablets because there's barely any data. So we map all of the system tables into a single DocDB tablet, and this form of putting multiple tables into one tablet is called co-located tables in Yugabyte, and you can look it up. There's a lot of documentation. Anyways, it's co-located, and there's one special DocDB tablet or table that deals with all the system catalog. And finally, internal DocDB tables all have the same format. They have key to document format, and the schema is enforced on top using the schema metadata from the system catalog, which is replicated across the different nodes in the cluster. Okay, so with that background, if we look at how this works, the entire system, you have a system catalog that comes up. This is a modified version of initDB that Postgres runs. So this initDB will actually bring up a distributed system catalog. If the client, say, connects to a node to create a table, it's going to find the tablet leader of the system catalog to record the schema. And this is going to get replicated into all of the tablet followers because you need high availability. And after, it's going to create the appropriate number of tablets for the table. So the table is sharded into tablets and they need replicas. So all of those are created. In this example, we have a table with 3 shards, T1, T2, T3, and the first node has T1 as the first node is the leader for T1, second node is the leader for T2, and third node is the leader for T3, and a replication factor is 3. At this point, the table is created and considered created and is returned to the client that, hey, this table is created. Okay, now we'll look at a quick insert data path. So in the insert data side, what we find is that the primary key columns of the SQL table become the document key. So you remember that DocDB tables have a document key and a document value, a document, right? So the doc key is really composed of all of the primary key column values from the original table. Each row maps to one document. So all of the different columns, non-primary key columns, they become an attribute in a document that goes into DocDB. If the original table in Postgres did not have a primary key, which Postgres supports, then a logical row ID is created, and it's kind of written using that logical row ID. Now, you could have indexes or like a unique constraint or a bunch of these things. All of them map to separate DocDB tables internally, and an update to the primary table becomes a distributed transaction, which we looked at before, across the primary table and the index table, right, internally. So like if you insert into a table with one index, the snippet shown here is how it would work, where it would begin a docdb transaction. It would insert into an index table. It will insert into the primary table. Of course, you may, if it is an update, you may have a delete of the original value and so on. Like you could have some inserts, deletes, and updates mix in here. But anyways, the whole thing is committed as a single transaction. All right. So DocDB only deals in terms of tables, and all relations from PostgreSQL are mapped into some form of table underneath. So if you look at the insert path, because everything is translated into an insert into one or more tables, and we're just going to look at the simple path, which is inserting into a single table, and you can just extend this for a transactional flow. The PostgreSQL upper half, the coordinator receives, like say, an insert from the client. This insert actually detects the tablet it belongs to. If it is a distributed, so Yugabyte also distinguishes between a single row and a multi-row transaction. And for the single row transaction, it opts for what is called the fast path, where it can completely avoid the transaction coordinator. For distributed transactions, there's no choice. You have to update multiple locations, so you really have to go through a transaction coordinator. But in any case, this is just showing you the fast path, or how a single row is updated. So the single row update actually goes to the leader of the tablet that owns the row being updated, and it says, hey, here's the update I want to make. The update could be a complete commit record, or it could be a provisional record in the case of a distributed transaction. That gets replicated to the peers. Once it gets replicated to a majority, the write or the operation is act, right? And if it's a part of a transaction, it's act only to the transaction handling layer, which then continues to do more operations and finally commits everything and responds to the client, right? Okay, so that's all I had. I mean, maybe I'll just go quickly through the conclusion, because we're almost here, and then we'll open it up for questions. So our aim was to really take PostgreSQL upper half, and I mean, we're a multi-API database, but we won't get into that. We took the upper half of PostgreSQL and the lower half of Google Spanner. Taking the upper half of PostgreSQL is motivated by Amazon Aurora, and Google Spanner is, of course, unique in its kind. It's Google Spanner, right? So we put those two together and created YugabyteDB as a open source database row, and hope you folks really find value. Like you can play with it. There's a lot more details on our documentation architecture side. We've written a few blogs about it. If there are any requests, please reach out to us. We always like to listen to what folks like to hear more about and write on those type of things. And finally, you can download and try this for yourself on your laptop. You can join our Slack if you have questions, and do consider giving us a star on GitHub. We really appreciate your support, right? Yeah, at this point, we can just open it out to questions, Andre.
Yeah, there is a question regarding regions. Can a table be distributed across several regions in YugabyteDB? If yes, can it work when connection between regions are unstable? For example, one of the regions is unavailable. Can users still use the table?
Yes, absolutely. I'm going to see if I can hit the back button far enough to actually go to the location. But yes, YugabyteDB can be deployed across regions. I think I will go quite a bit back. I don't want to hit escape because I might not get the present button again. But yes, YugabyteDB can be deployed across regions. If a region fails, it automatically takes over. This is what was shown in the how it's practically deployed section, right? So this section actually talks about how YugabyteDB is deployed across. This says 3 zones, but for all practical purposes, this might be regions also. That's completely fine. And this covers what happens on a region outage, right? So that's and even if there are network blips, because it's Raft, you always just need a majority of acts from the system. So if one of the regions is running slow or is network partition temporarily, there's still 2 other regions that can take that can keep making progress.
Okay, thanks. So far, there are no more questions as far as I can see, but if you have anything, guys, please ask. Okay, let me kind of follow up. So in this particular scenario, even the outage in the entire region, you can still continue with reads and writes, correct?
Yes. So you can totally continue reads and writes. So note that you need only the nodes with the solid boundaries to process reads and writes, and you need one other guy to exist in order to continue writes. So for reads, you need only the guy with the solid boundary, and for writes, you need the solid boundary cylinder and one other guy, right? So, and in this case, if you look at what happens after the failure, if an entire region or zone fails, you find that it quickly switches over in 3 seconds to somebody else, and now the invariant is met where every colored tablet has a solid boundary that's available, and everybody has at least one other guy to which he can write. So Raft lets you make progress. So yes, you can continue doing reads and writes. You'll get a 3-second or so blip, and after which things will just stabilize and continue. And if
but
you're,
in the case of, like,
if you're, yeah. Go ahead.
In the case of full region outage and the single node failure, you will still have read access to, like, the entire table, like the most of the table will still be available, but the part which has only one node will be available only for reads, right? Did I understand it correctly?
Yes, I mean, yes and no. So like the answer is it depends. If you lose an entire region and you lose a node simultaneously, right? Like, so within the same 3 seconds, right? Like we're assuming that, yeah. So in that case, then let's say we lost node 7 and we, in addition to the entire region, then this pink guy will not have enough replicas to elect a new leader, right? So until node 7 comes back and we are able to elect a leader, because node 2 will not know if it is simply partitioned from node 7 or if node 7 is completely down. It wouldn't know that. So you will not be able to do writes or read from a leader. What you can do is read from the follower. However, the suggestion to handle 2 simultaneous failures, this is what this would be called, is to go to replication factor 5.
Yeah, I understand that. I'm just thinking of scenario like if it's like major outage with the region and you still have kind of background noise of single node failures, you'll have like a partial unavailability in terms of data. So like, and you'll still have some data available for reads, even though like 2 nodes out of 3 in the Raft group are failing.
That's right.
Okay.
That's right. So yeah.
But if you want to address like 2 node simultaneous prolonged failure, like 2 regions or a single region and a lot of single nodes failing, you obviously need to go to replication factor of 5, more regions.
That's right. Yeah.
Availability zones or whatnot. Okay, we're close to be out of time, so I suggest we move to the Zoom Q&A group. And we'll continue with questions there because the questions are coming. Yeah, there are 2 more questions.
Yeah, thank you very much, folks. See you there in the Zoom, and I guess it's time to the closing ceremony of the conference. Thank you very much for your talk, Karthik, and thank you, Andrei, for supporting with Q&A session. See you there.
Yeah.
Bye.
Yeah, thanks, folks. Thanks, Andrei. Yeah, thank you. Thanks, everybody. This was great. Thanks for